Taking a look at some more core pure revision today, we're going to take a look today at first order differential equations. So, if you can't remember, a first order differential equation is just a differential equation of the form where the derivatives involved are just to the power of 1. So, for example, it'd be dy by dx, for example, plus 2xy, might be equal to x, for example, right? So, it's first order because it's a power of 1 there. A second order would be something like dy squared by dx squared, or d squared y by dx squared, plus, something like 2xy equal to x, for example. So that's the difference between a first order and a second order there. Okay, so in this video today, we're only taking a look at the first order differential equations. So these are the differential equations of the form where you need to solve it using an integrating factor or by splitting the variables. Now, splitting the variables is not rare, but it's more of an A-level topic rather than a further maths, but it still can pop up, so I've included a couple just to illustrate it. So let's jump into these. Now, these are all taken from the Core Pure 2 book, apart from a couple of exam questions which you'll see later on in the video. So let's jump straight into this one. Exercise 7a, question 4. So question 4a. So we're asked to find the general solution to the differential equation dy by dx plus 2xy is equal to e to the minus x squared. So 4 marks for this. Now, because it's in this format here, so when you've got a differential equation of this format, so dy dx plus py is equal to q, because it's in that format already, all we need to know is find the integrating factor. So I'm just going to call it, throughout the video, I'm just going to put if for my integrating factor. So the integrating factor, well, to find the integrating factor, we do e to the integral of p of x, or py in this case, so I'll call it p of x dx. Okay, and your p of x is this middle coefficient here. So it's the coefficient of the y, which is, in this case, 2x. So I want to find e to the integral of 2x, so the integral of 2x dx. And this is a nice easy integration. Add 1 to the power divided by the new power. So this will just give you e to the x squared. Okay, so now we can start solving this differential equation and finding the general solution. So my general solution, well, we find the general solution using this form here. Well, to find the general solution, we say the integrating factor, so e to the integral of p of x dx multiplied by y is equal now to the integral of the integrating factor, so that's e to the integral of p of x dx times by q, which is the last bit here. So in this case, it'd be the e to the minus x squared times by q. So if we apply that now for our question here, well, my integrating factor we've already worked out, so that's ex, so it's e to the x squared times by y, which is equal to the integral now of e to the x squared multiplied by e to the minus x squared. Okay, well, these here are just going to give you 1, right? So e to the x squared times by e to the minus x squared, add the powers, it'll be e to 0, which is 1. So we can write this now as e to the x squared y is equal to the integral of 1 dx. Well, the integral of 1 dx would just be x, so this is e to the x squared y is equal to x plus c. Don't forget your plus c, very important, because it's a general solution, so we need that plus c there. So, because this is e to the x squared, y is equal to x plus c, well, we want it to be the general solution, so we need to get it in terms of y. So therefore, the general solution, so if I do it up here, so my general solution will be y, dividing through by the e to the x squared now, so that'll be x plus c divided by e to the x squared. Okay, now you could write that as, so that could also be written as x e to minus x squared plus c, and then again e to the minus x squared. Okay, but that would be fine there as well. But just so you can see it as another way that would be how we could also write it. And then in part B, for 1 mark, we're asked to describe the behaviour as y as x tends to infinity. So to consider that, we need to look at our general solution. So if we look at our general solution here, well, imagine what happens is, as x tends to infinity, so as x gets bigger and bigger and bigger, okay, so my numerator, I can't speak, is going to get large, but my denominator is going to get very large, right, because this is the exponential function, it's e to the x squared. So you put a very large number into here, and you can test on your calculator, right? Put a number as a numerator, divide it then by a very, very large number, and what you'll see is that it tends to 0, okay? So because the denominator is much larger, what it means is that y is going to tend to 0. So if we just clear all this, what this means now is that as x tends to infinity, so part B, so as x tends to infinity, so as x tends to infinity, the denominator will become much larger. The denominator will be much larger. So therefore, this implies that y will tend to 0. Okay, and that's simply all we've got to say for that last mark there. Okay, so that's our question done. Again, another question from exercise 7a here, this time question 13. So we're asked to find the general solution to this differential equation, and then part B wants us to find a particular solution. Now this is a differential equation, which is one where you have to split the variable. And the reason we can tell that is because it's not in the form that we need for an integrating factor. So, and because it's still a first order, we're not going to be doing anything like we would for a second order differential equation. So all I've actually got to do is split the variables here. So because there's a y cos x here, if I divide through by the y, so part A, this will be 1 over y dy dx. So that's going to be equal to cos x. Now if I integrate both sides here, so the integral of 1 over y dy dx, that's going to be equal to the integral of cos x dx. Now simply the integral of the left hand side will just be ln y, and the integral of cos x, well, that'll just simply be hyperbolic sine of x, so hyperbolic sine of x, but don't forget your plus c because we have a general solution. Okay, so all I've got to do now to actually get this in terms of y, I just have the antilog, right? So that would be e, take antilogs both sides, so that'd be raising everything to e, so that'd be e ln y, so that just gives you y, so that'd be equal to e to the power of hyperbolic sine of x plus c. Okay, so that's my general solution there, because we've got it in terms of y already, so we don't have to do anything else. Now for part B, we have to actually work out a particular solution. So we're asked to find the particular solution which satisfies the condition that y is equal to e when x is 0. So when x is 0. Okay, so don't forget we use the general solution for this, so y is e, so e is equal to e to the hyperbolic sine of 0 plus c. Well, what I've got now is e, well hyperbolic sine of 0 would just be 0, right? So that's e to 0, which would be 1 plus c. So what I've actually got here is just e to the c now. But if e is equal to e to c, remember that's e to the 1. So in that case, c just has to be 1, right? Because of the same base, the powers have to be equal as well. So c must be equal to 1. So in that case now, my particular solution, so PS, is y equals e to the hyperbolic sine of x plus 1. And that's simply your last 2 marks there. Okay, so that's an example, like I said, where you've got to split the variables. Not as common on the further maths modules, but it is still there, so it's just worth including a question or two for it. Okay, so let's move on to the next one. This time now, we're looking at a question from the old Edexcel further maths spec. So this used to be on the FP2 modules. And what we've got is we've got to find a general solution and then a particular solution. So this is quite a common style of them. Find a general and then find a particular solution. So question 5a. We've got x dy by dx plus 2y is equal to 4x squared. Now, before we can get the integrating factor for this, remember we always need the coefficient of dy by dx to be 1. In this case at the minute it's x, so to get it as 1 I need to divide through by x. So dividing through by x, that'll give me dy by dx plus 2 over x times y, and that's equal to 4x squared divided by x, that'll just be 4x. So now we've got this in the correct form. Now we can work out our integrating factor. Okay, so my integrating factor, remember that's e to the integral of my middle coefficient, so the coefficient in front of the y, so 2 over x dx. And remember, the integral of 2 over x, that would be 2 ln x, so this is e to the 2 ln x, which we can rewrite this as e to the ln x, then this is all squared. So what this actually gives me is just x squared. Okay. Well, now we've got our integrating factor. For a general solution, remember, we do the integrating factor times y. So x squared times by y. And this is equal to the integral of the integrating factor, so x squared, times by my last term, which is the 4x squared dx. Simplify this expression here for the integrand, so this would be x squared y is equal to the integral of 4x cubed dx. So now we can actually perform the integration. So x squared y is equal to, add 1 to the power divided by the new power, so this will be x to the 4 plus c. Okay. And then simply, just to get this in terms of the general solution, I need to divide through to get y on its own. So to get y on its own, I've got to divide through by x squared. So y is equal, so it would be x to the 4 divided by x squared, so that'll be x squared itself. And then it'll be plus c over x squared. So, or you could write that as c to the x, c times x to the minus 2. Okay. And that gives me my general solution there. And then part B, I'm just going to try and do it over here just so we can see the actual general solution on the screen. Part B asks us to find a particular solution for which y is equal to 5, x equals 1. Well, if y is equal to 5 x equal to 1, all I've got to do is just literally sub them values into my general solution. So 5 is equal to 1 squared, so 1, plus c over 1 squared, so that'll just be c over 1. Okay. Well, c over 1 is just c, so what I've got now is c plus 1 is equal to 5. Well, c just clearly has to be 4. So my particular solution here now is going to be y equals x squared plus 4, because c in this case is 4, over x squared, because remember it's x to the minus 2, which is the same as c over x squared. And that's it. So you can see these questions, once you've got enough practice with them, they're all pretty similar, and there's nothing that can really catch you out as such. Okay, so if that makes sense, let's move on to another exam question. Now this one's a little bit trickier, and you'll see why it's a little bit trickier in a second, but the basis of the question stays the exact same. Okay, so we've got to make sure the coefficient of dy by dx is 1. So question 3. Well, to get that in, it's the exact same as the last one. I've got to divide through by x. So that'll be dy by dx plus 5 over x times y, and that's equal to ln x over x divided by x, so that'll be ln x over x squared. Okay. So now we can work out the integrating factor. So integrating factor is e to the integral of 5 over x dx, and that'll give us e to the power of 5 ln x, which we can rewrite as e to ln x all raised to the power of 5, which is equal to x to the power of 5. So we've got the integrating factor now. Now we need to get the general solution. So remember, the general solution, we always do the integrating factor, so x to the 5 times by y. This is equal to the integral of the integrating factor, so x to the 5 times by my last term. So this is ln x over x squared dx. And you might be able to see now why this is going to be a little bit trickier for this question. And it's because of this integral here. I've got x to the 5 times ln x over x squared. Well, we can simplify this a bit, right? So this is going to be, do it over here, this will be x to the 5 y is equal to the integral of x cubed ln x dx. So this is why this is tricky now, because I've got to do this integral here where I've got two functions. I've got x cubed and I've got ln x. So we're going to have to integrate this by parts. So we need to set up our u and our v, so or our u and our dv. So dv by dx. Well, remember, we want to pick, or we want to make life easy for this integration. So I'm going to have a du by dx as well, and I'm going to have a v up here. Well, the trickiest bit here is this ln x. Now, if I pick ln x as my dv by dx, that's not particularly easy, because ln x isn't particularly easy to integrate. So I'm going to pick ln x as u, so that I can then differentiate it. And I'm going to pick my dv by dx as x cubed, because x cubed is nice and easy to integrate. Okay. Well, the differential of ln x is 1 over x. And then the integral of x cubed will be, so add 1 to the power, so that'll be x to the 4, and then divide it by the new power. So that'll be divided by 4. So now we can perform the integration. So this is going to be, we do it over here just so I've got enough room. So this will be x to the 5 times y. Now this is going to be equal to, so remember the formula for by parts, this is going to be uv, so u times v, so that's going to be x to the 4 over 4 ln x, minus the integral now of v and then du by dx. So v is x to the 4 over 4, so x to the 4 over 4 times 1 over x. Okay, dx. Well, this would simplify now to give you x cubed over 4. So this is x cubed over 4. So just right underneath x cubed over 4. Well, the integral of x cubed over 4, so you add 1 to the power, divide by the new power, so that'll be x to the 4 over 16. So if we rewrite this out now, so I've kind of run out of room, so what I'm going to do is I'm just going to rub some of it out. So we'll just get my razor. So if we rub the top line out, we should have enough room to finish this question, I hope. It will get rid of this line as well. Okay, so let's just finish this off now. So what we've got here now is the integral of x cubed over 4, that's equal to x to the 4 over 16. Okay, so what we've got here now is x to the 5 times y is equal to x to the 4 over 4 ln x minus x to the 4 over 16. Okay, so this is quite a long question, and don't forget your plus c, right? We need the plus c because it's a general solution. Now I want this to be in terms of y, so all I've simply got to do now is divide through by y. So therefore y is equal, well, imagine I divide this term by x to the 5. Well, I've got an x to the 4 as a numerator. Well, all I'm going to get left with is a denominator of x then in that case. So this is 1 over 4, or ln x over 4x. Okay, so I've divided x to the 4 over 4 times ln x by x to the 5. So the x to the 4 will cancel with this x to the 5. That'll just leave with an x on the denominator. And my ln x I'm going to take onto the numerator like that. Okay. Minus. So again, we've got an x to the 4 here. So that'll just cancel, and I'll get left with an x on the denominator. So that's minus 1 over 16x. And then finally, if you've got a c and you divide it by x to the 5, that'll be c over x to the 5. And there we have it. So that's my general solution for that question. So quite a long question there. And it's very easy to make a mistake with the integration by parts. So that's why that one is a couple of extra marks for your general solution. So there we have it. So that's my general solution. So another question now, mixed exercise 7, question 4. A pretty standard question, quite a nice easy one actually. Comparing this as 7 marks to the last one for 8, this is a much nicer question. So it's already in the format to work with as well, so we don't even have to do any rearranging. So really quite a nice question. So if we work out the integrating factor straight away, so that's e to the integral of, this is y over x, remember that's 1 over x times y, so that'll be 1 over x dx, which would be equal to e to the ln x, which we can just write as x. Okay, so I've got my integrating factor. Now all we need to do is do the integrating factor times y, so x times y is equal to the integral of the integrating factor times by the last term here, which is the root x, so that'll be x to the half dx. So now this is x to the 1 times x to the half, so we can write that as x to the power of 3 over 2, x to the power of 3 over 2. Integrate this, so add 1 to the power, so that'd be 2 over 2, plus 3 over 2, so that'd be 5 over 2, and then divide it by that. Divided by 5 over 2. I've got my plus c, and remember we can simplify this. If you divide it by 5 over 2, the 2 will times by the x to 5 over 2. So what I'm actually going to get here is xy is equal to 2x to the 5 over 2 divided by 5. And then don't forget your plus c. Okay, so never forget your plus c, very important, because obviously it's a general solution, right? So we need that plus c because it's a general solution. And then finally, to get this as a y as a function of x, I just need to divide through by x. So y is equal, dividing through by x here now, so that'd be x on the denominator, but that'd be x to the 1. And remember the rules for indices, we'd subtract 1, we'd subtract the powers, so that'd be 5 over 2 minus 2 over 2, so I'm going to get 2x to the 3 over 2 divided by 5 plus c over x there. Okay, or you could write that as c times x to the minus 1. Both are absolutely fine, so whichever you prefer. And that's it, so we've found y as a function of x for that one. So 7 marks for that, believe it or not. Much nicer than the previous question. And then let's finish with the last question here. Again from the mixed exercise, from Corpio 2, question 11. So you might recognise this being very similar to the, I think the third question we did today, or maybe the second one. So it's one of these where you have to split the variables again. So question 11, part A. So we've got dy by dx is equal to y times hyperbolic sine of x. Okay. Well, if we split the variables here, we're just going to divide through by y. So this is going to be equal now to 1 over y dy dx. So this is equal to hyperbolic sine of x. And now we need to integrate both sides. So I'm going to integrate both sides here. So the integral of the left hand side, that'll be ln y. The integral of the right hand side, well, that's just going to give me cos x, right? So that'll give me cos x. But don't forget your plus c. Again, we can't forget that plus c. And now we just need to anti-log. So raise everything to the base of e. So that'll be y equals e to the cos x plus c. And that's simply it for my general solution, okay? So that's my general solution. And just like we did before, we have to find a particular solution now for this. And this is when y is equal to 1 and x is equal to 0. Okay? So using our general solution, can we obtain a value for this? Well, what that would be saying then is that 1 is equal to e to the cos of 0, plus c. Now, you should be aware of the fact that cos of 0 is equal to 1, or just work it out using the exponential functions. This is equal to 1. Now, I've got e to the power of something, it's going to be equal to 1, so that power clearly has to be 0. So I'm losing my voice as well. Hopefully I'll make it to the end of this one. So, if I just rewrite this, so this is e to the cos of 0 plus c is equal to 1. So remember, anything to the power of 0 give me 1, right? So this power has to be 0. So at the minute, this is e to the 1 plus c equals to 1. Well, this has to be 0. So my c must be minus 1, right? For that to be e to the 0. So c is minus 1. And if I write that as my particular solution, it's going to be y equals e to the cosh x minus 1 there. Okay, and then that's my final 2 marks. So that brings us to the end of this video. I hope this has helped with first order differential equations. I'm going to do a follow-up video on second order differential equations, and I also want to do one on coupled differential equations as well. So if you're new around here, be sure to subscribe, or you're looking for more further math content. Leave me any feedback, anything that you'd like me to go through, just leave it in the comments below. But yeah, cheers guys.